So welcome. I'm a new professor here in computer science and engineering. Very excited to be here. And my work lies at the intersection between computer science and math. And really, all of computer science is founded upon the mathematics of discrete objects. So rather than say calculus and differential equations and things like that, eventually, yeah, I hit the lights. I'll go to sleep.
No sleeping. I'll come after on the show.
No, I'll take a nap while you're at it. And so, what I'm going to try to do in the brief time we have here is kind of share with you some of the passion and fun I have with computer science, and also I'm going to start off kind of giving you an overview of what computer science is, computer science and engineering. And forgive the date, that's when I wrote the slides, just yesterday and not today. So it's a very personal introduction to computer science. So I'm going to share with you both my work and the fun I get to do with computer science. I take my work and make a hobby out of it as well. So in computer science, we use math and logic and other theoretical tools to build things. We think of computer science not so much the science of computers, but we use computers as a tool, much like an astronomer would use a telescope. We use computers to peer into, well, what can we do? What can we compute? What can we make happen computationally and create new methods and new ideas for solving problems? And these ideas we come up with, we sometimes we publish them and write about them in software. For me, software is a mechanism to get my ideas out to the world, to get them to use these ideas. So for example, I write solvers for solving matrix equations. So x plus y minus z equals 3, and 3 equations. You've done maybe some of those? Okay, that's all I do for a living. Sounds exciting. Well, it is. In fact, I just solve with bigger systems of equations, not 3 by 3, maybe 3 million equations and 3 million unknowns, just bigger. And then I create new methods for solving these problems, and I get them out to the world to use. For example, anyone here use, I think it's Google Street View? Ever use that? Okay, well then you're using already the results of my research, because Google, when they drive their car around, they take photos. And these photos, though, they get GPS coordinates for these photos, but the GPS coordinates are noisy. And if you were just sort of to plunk down those photos where they would lie, it would look like a mess. I lost my pen. You might have done this in a science experiment. You get a bunch of data, and you say, oh no, that's not what it's supposed to look like. It's supposed to look like that. And so we've got to put these photos in the right place. It turns out that's a really large matrix problem, and to solve that problem, they call my software to do that. So every photo in Google Street View goes through my solver to do that. That's just one example of what I do. And so we use math and logic to create these ideas, to create these methods, and create these new methods, and sometimes we write software that expresses those ideas. So for me, software is sort of like a typewriter is, if you know what that is, or a paragraph is, or a sentence is to an English major. So they have ideas, they want to express them, they express them in written prose. Well, we express our ideas in software. The kind of logic we use is the logic of discrete objects. If this, or discrete logic, if this, then that. What can be computed and what can't? What is information? How do we manipulate it? I've got a pile of rocks here on my desk. I keep it on my desk, and I use these actually in my research, believe it or not. I'll create methods that I'll be thinking of methods in software to say, okay, let's use this to represent something I'm trying to compute. And one thing we do in computer science is things like counting questions. Well, I have 8 rocks in my hand. How many ways are there of, say, picking 2 of them? And that can give an answer to some of our computer science questions, some of those parts of logic that we deal with. In practice, what we do is we create algorithms, we create software. An algorithm is simply a step-by-step procedure for solving some problem. Software then makes that algorithm work on a computer. And it's kind of like a novel. Software is like a novel. An algorithm is like the plot line of that novel. It's like the method, the process of how it is. And the novel kind of makes that plot line go, makes it happen. And as I said, we use computers as an end, or not as an end, but as a tool, just like an astronomer uses a telescope. Although computer engineering, computer architecture, they actually look at building things. So different kinds of problem domains in computer science, artificial intelligence, robotics, Siri, for example, on the iPhone. You talk to her, and she gives you answers, and it's an amazing tool. Architecture, design, graphics, visualization. This is one of my hobbies. I don't do much of these. I do this right here. It's called computational science. I make happen the mathematical models that simulate the real world. So one company that's using my solver is wanting to know the question, okay, I have a chip. They have a chip. Millions of transistors. And they want to send this to a fabrication factory to build this chip. Those factories cost $1 billion. To make a chip takes days and weeks and months to actually come back with a chip. And then, oh great, and they plug it in. Oops, oh it didn't work. Try again. Another month, another millions of dollars. They can't do that. So they simulate these chips first on the computer to ask, well, hey, will it work? We can try that. They can try that on the computer. Well, to ask the question, will it work, they need to solve a system of equations, and they call my codes to do that. And one recent work I did for at a consulting project for about a week worth of effort, I came up with a new idea, that new algorithm I was telling you about, a new method for solving their problem. And suddenly they cut the time to solve this problem from, say, 8 hours to 4 hours. So they send the chip out, and they say, hey, will it work? And they get a question back this afternoon instead of tomorrow. That's a big win, just by using a new method for solving that problem. So that's the kind of stuff I do. And where my work lies in particular is in this intersection of two different domains of computer science. Okay, I've got over here things like this. This is a graph. So you know Facebook, right? Mm-hmm. Imagine this is 4 people in a Facebook graph. And person 1 and 3 know each other. And 2 and 3 know each other. And 2 doesn't know 1. Okay, this thing you can also write down, if I could have the lights on just briefly, as representing a matrix. So you can have a matrix that this Facebook friendship is capturing. Imagine equations being friends with each other. Okay, so imagine the first equation has maybe positions 1 and 3. So person 1 knows 1. Make a table of your friendships. Okay, person 1, 2, 3, and 4. Person 1, 2, 3, and 4. And so person 1 knows themselves, and person 3. Person 2 knows 3 and 4, like this, and themselves. We'll put the diagonal there to make it a nice matrix. Person 3 knows everybody, and person 4 knows 2 and 3, like this. So this is a matrix, and those little x's I drew or maybe this is a formula x plus z equals 4. And this is an equation with maybe x, y, maybe w, 3 other variables. And this is all the variables. And this is just 3 of them. So most of the time when we come up with these equations, just like that circuit problem or Google, not all the equations have all the unknowns. And so you get this structure like this. Not everyone on Facebook knows everyone on Facebook. And now we deal with algorithms to follow this graph and say, well, hey, how far away is node 1, person 1 from node 4? Oh, it's 2 hops away. And those kinds of questions of counting and how far away. Have you ever used Google Maps? No, I don't. You probably used, like, go from here to Houston back. Use a map program. Well, that's a classic problem in computer science. They model the road network as like a collection of these links. This is a graph with say roads and intersections, and you want to know how to get to Houston. Well, now you got to follow this path in a graph to answer that question. So part of my work lies over here. The other part lies over here in solving these matrix equations. And I put the two together and I make these things happen. These are just a small snapshot of the companies that use my solvers in making these methods work and getting them out there in the real world. Now, to give you, these equations are also, let me show you this back again. So, they're also beautiful. This is a way of writing 4 equations and 4 unknowns and how they relate to each other. Okay. Well, if you have 3 million equations or 30,000 equations and 30,000 unknowns, we can draw this too. It's just bigger. Okay. Now to draw the thing, we get pictures like this. And this is an article that appeared, and you can turn the lights off now. This is an article that appeared in fastcompany.com, the webpage of the magazine, entitled Geeky Science Problems Double as Works of Art. Sparse matrices, a lot prettier than they sound. And then the first thing it says, the work you see here is so pretty you'd hardly guess it's the product of some of the world's biggest math nerds. Okay, so the way we draw this, imagine these Facebook friends back a page. Okay, if you just had this list, oh, you know, person 1 knows person 3, they're their friends, and 3 knows everybody, and 2 knows, and so you just have a list of people and their friends. And then you might want to draw it, look at it. Well, how would you do that? I mean, that's okay with 4, but what if you had 400 or 4,000? How would you draw it that it made any sense? Well, one way we can do this, and we do this on the next slide, is with a physics simulation. So imagine putting a positive charge on each of these balls here, each of these people. So people repel each other. But the links pull them back together again, like a rubber band. And so if you had 2 people with a rubber band between them, if you pull them too far away, well then the rubber band will pull them back in. And if you push them too close together, the charge between them will push each other, and they'll reach an equilibrium. And 3 friends would reach an equilibrium, and maybe the 4th one who knows just person 3 would fall into this form. And if you had more, it's drawn this way, where now the edge color represents how tight those rubber bands are. And this is a problem then that we drew. I collect, some people collect baseball cards. I collect matrices. I collect, you know, x plus y equals 3. Ooh, that's pretty. Well, it is. Okay? It is beautiful. And they come from all these different kinds of applications. This is just one of them. Here's matrices from my collection. Okay, this is something called a Hessian matrix. Here's a financial portfolio optimization problem. You want to know if stocks go up, if bonds go down, if your rates go up or your rates go down, what kind of portfolio do you want to balance? That's a matrix problem. You solve that, and you earn a lot of money. I don't solve those problems, somebody else does. Here's a simulation of Charleston Harbor. Where is the pollution flow? You get this sort of shimmering mesh-like structure. And this is no different than this picture here, just bigger and drawn in color. That's all. So these are just equations, just math. It's all just math. Here's what my student did. This is about 500 people and about 300,000 web pages, and you have to draw a line between them if that person likes that web page. And it's sort of a poppy-shaped color because this person likes a bunch of web pages that nobody's ever heard of except for them. And here's a whole smattering of web pages that everybody likes, and this is probably a bot that likes a whole bunch of random stuff that nobody's even heard of, and it's huge. No, well, that's probably not a real person. And you get this beautiful shape just from a bunch of equations, a bunch of relationships. And in computer science, we like to work on problems like this. This looks like an orange fishy, but it's actually a matrix that comes from a circuit problem. You want to know, hey, will this chip work? Well, that's what it looks like if you simulate it with a bunch of equations. So this is another application of my work, the same sort of problem with Google. The U.S. Geological Survey wants to make maps of, say, the Mercury or the Moon or Venus. Well, Venus, that's hard to make a map of. But this is maybe the Moon. And they've got a bunch of photos, and you'd like to not have this. You'd like to draw it this way. You'd like to stitch those photos together nicely. Well, you could do that manually with thousands upon thousands of pictures just sitting there. That's nuts. We create algorithms for solving those kinds of problems. That's what computer science does. So this is an example of image processing and graphics. But here again, it boils down into a system of equations because we want to know, it turns out the same thing with Google, you want to stitch those photos together. So you walk through Street View, the photos smoothly go from place to place and you don't have a jarring gap between them. You need to solve the matrix equation. So the U.S. Geological Survey is using my code to do that too. And I'm recently working with Nvidia they're also interested in this. This is a domain of high-performance computing. You solve these matrix equations really fast because they drive physics simulations, for example. So Nvidia supports my work. They provide me free hardware and funding. And it's all about taking these matrix problems and putting them onto the GPU, getting the GPU to do them faster than we could before. And now what I want to do is show you some of the tools I use to come up with these methods. Now, this is where this pile of rocks comes in really handy. It sounds kind of strange, but I'll actually get inspiration from this pile of rocks here. You can't really see it. Can you turn the light on? They're really pretty. They come from the same beach in California, just one beach, all these different colors. And so what I do, when I've got these equations to solve, I might have something like this. I've got, say, here I've got 8 equations and 5 unknowns. Okay, and what I'll do is I'll play a game of Mancala. Okay, I'm trying to create a parallel algorithm. So imagine I've got 8 rocks. Okay, each rock is going to represent one of these rows. This is an equation in my matrix, and this equation is missing something. It's missing the first unknown. Okay. And my goal at the end of the day is to have a system that's in upper triangular form, reduced into upper triangular form, so that I can solve it backwards, knowing then finally what the last variable is. Okay. So to do this, I want to do this in parallel, because this GPU hardware has thousands of things it does all at the same time. Like an army of workers all working together. You've got to orchestrate this, and we have to design, in computer science, we have to design the algorithms to make these all workers all do the right thing just at the right time. So how do you think about 1,000 different things happening at the same time? A pile of rocks. Okay. Imagine now that I have these 8 rocks, and I'm going to take the first 6 rocks and put them in a pile. And they're in the same pile because they all have the first unknown in it. And these 2 I'm going to put in the next pile. Now, what you can do is you can take 2 equations, okay, and from one pile, like 1 and 2. And I can take this equation and eliminate an unknown. Solve for this equation for the first unknown, right? Substitute into the second one. And then I remove this, make that 0. That means I pick up 2 rocks, I annihilate this, and I put it in the next bucket, just like a game of Mancala. I pick up 2 rocks and put one down here and the next one down there. And at the same time now, someone else can come along and play this with me. Grab 2 rocks and put them down, and grab 2 rocks and move one down. And eventually, we just keep playing this game. We've got 1 rock per bucket, and it goes through like this. So I've got 3 hands playing at the same time. And after those 3 play, they have to solve the rest of the equations, and so forth. And finally, at the end, we've got 1 equation in each bucket, and now I know what this variable is. And now I can substitute back and solve for that one, and so forth. So with these rocks, I'm mimicking what my algorithm does, and I gain inspiration out of, oh yeah, I see how I can do that. And I'll actually sit down and I'll have these rocks on my table, and I'll move them around. I'll typing away my algorithm on the computer, and I say, okay, now what can I do? Oh yes, I can do this. And that represents the state of these equations with a pile of rocks. So that's what I do as far as my matrix equations. Okay, what I want to show you next is something really cool that I've been doing since about June. So these pictures, like this, have generated some interest in the popular press. This is fastcompany.com. And I got contacted about last June, or June of last year, by an ad agency in London that said, oh, these are really beautiful. Can you do it for music? I thought, oh, that's crazy, music. So I thought for a little while. And I thought, okay, yeah, I could. They wanted to draw a whole piece of music at once. I thought, okay, well, I know this is pretty. That's a graph. All right. Well, I know that like this is pretty. This is a mesh. That's really pretty. Well, how would I take this and create some rules? So I want to take a piece of music, and slice it and chop it up into pieces and use what's called a Fourier transform. You know, like an equalizer, you see the different bands going up and down? Well, we can do that, and we can extract frequencies. We get notes out of the music. And then from the notes, I now have a discrete set of notes like fingers on a piano, like these little discrete things, and I can say, oh, this note is a friend of that note at this moment in time. Okay, I can do that. And I said, sure, I'll give it a try. You know, would you like do this for commission? And I said, sure, but you know, we haven't seen anything yet. And I said, okay, I'm intrigued. I'm going to give this a try. And so 1 week later, I came up with this artwork right here, which, let me play you the music. So this is a matrix. But in fact, it's a matrix that comes from, oh, I'm sorry, I'm going to plug this in. This is just a bunch of relationships, right? But you can draw it. And now here, the lines, the blue is low notes. So the music is starting here. It's all low, it's all blue mostly. And pretty soon, and it's very regular and repetitive, just like a crystal. The rules are just repeating. And suddenly, it wakes up right here. Now the music is spinning down here, and I should draw this in time like a video. And now it's going on the higher notes here are red, are higher frequencies. The low is blue, in the middle is yellow. Lights around here like this. And they thought, oh, this is cool, like this. So I drew this for them as well, a different way of slicing and dicing the music. So they liked this one better, and they cropped this, and they made this this appeared. There's the author of or the band New Order that did Blue Monday. Anybody know Blue Monday? So that's the author. That's the creator of this music, and that's my visualization. It was for the artwork for the whole festival. For this one art for the whole weekend. And the music you're hearing here has a very similar structure to it. It's this one. When they sent me this music, it looks like a dead, like a frog or something. Well, they sent me this music and said, well, we like the first 30 minutes, 30 seconds of it. Really cool. This is the first 30 seconds of the music. It's got this really interesting structure to it. It's lighter blue. It's not much blue. Well, last song you heard, a lot of really love this. It's just lighter. It's this lighter color blue. The song is Blue Monday. Now, what's really interesting about this London Electronics Arts Festival is all of the music there at the festival was similar kind of electronic, boom, kind of music, and so it all built up this blue crystal tubes. Like all of these four came from the festival, and they're all very similar genre. They're different musical styles for different songs, and they're all, say, very different from, oh, I don't know, this one, which is a different piece entirely. Which is coming from, I think, his frequencies. And you don't see a lot of blue and heavy kind of thing. So I don't get this one. So you can just look at this and think, oh, well, that's not going to be some heavy bass beat. And in fact, it isn't. This thing is a piece by Bach. Totally different from the others. But something of the music is coming through this drawing. It's just like a collection of friends on Facebook. Okay, and here the friends are kind of scattered all over the place because the music is so complicated. Whereas a piece like this is so simple, it's almost boring. That's about it. That's about the whole song track. Just going over and over like that. And so you just get this. One very simple, that you've heard the whole track now. Oh, they're different, changed just a little bit, yeah. But very simple. And so they, anyway, different genres of music is totally different kinds of totally different sorts of music. But again, if you look at this, you think, oh, what kind of music is that going to be? Well, that's going to be
Strauss.
Yeah, it's also Fusto. Orchestral piece. So, but it's all computer science. 2001 Space Odyssey. That's what this is. It's all about you can turn the lights back. So it's all about, there's a theme here. It's all about creating new processes, step-by-step procedures for converting one kind of information into another kind. Here I'm creating music into art. Before I was converting noisy GPS coordinates of photos into some smooth thing stitched together. Okay? It's going from one thing to the next with a sequence of rules using logic like this. Well, if I have two rocks, I can do this. If I have one rock, I can't. But if I have no rocks, I can do something different. And you get different kinds of methods called algorithms. And then we say, okay, now that will work. Let me write the software to do that. And then I deliver the software to the world, and that's what we do. And it's one of the things we do in computer science. So I should have mentioned at the beginning, feel free to stop me if you have any questions. I forgot to say that. So now let me ask you. Now, if you have any questions or anything you'd like to ask about at all.
So you can do that to any song you wanted?
Yeah, I even did it to, I Have a Dream. I did it to Martin Luther, yeah, on Martin Luther King's speech. Yeah, it didn't look like, I didn't get blue mesh socks. I got this yellow thing, because his voice is sort of in the middle, range. But it was rather rhythmic. It was rather rhythmic, so I did get some interesting structure out of it. That was pretty cool. Yeah?
How did you choose the colors for each part?
The colors. Okay, so all I did is I took the piano keyboard and I dropped paint on it. Out on the computer, okay? So I put red on the highest note, and then so I've got the color rainbow, right? Red, yellow, green, red, orange is in there, right? Down to blue. So just red down, red, yellow, green, blue, red, orange, yellow, green, blue, whatever. And then if I find a note in that frequency, that's a line in the figure. So that's a line. So this is a low note. And so this piece right here you're seeing, then, you can look at that and say, ah. So it starts out with a lot of low blue notes, but not that mesh-like crystal thing, because this doesn't have that repetitive. It's fine. And then you get some higher notes. I think it's actually coming from the other side. I should add, each of these pictures is the same piece of music. It's just, I can slice and dice this music in different ways, and I get a different picture. In fact, when I draw this, I draw thousands of images, and then I just sort of pick and choose the ones I like. But the color, as I said here, it's coming in blue, low notes, and then suddenly, ba-da, you get the higher notes, higher frequencies at the end.
Did you use what software?
Oh, I wrote the whole thing. Oh, what language? Oh, MATLAB. For the one, and I did use a tool called, the same tool we used, a colleague and I used for drawing these matrices. This is in C++. But when I converted music into the graph, I used MATLAB, and which is a very high-level prototyping mathematical language. So I was able to do this in a week. But I wrote the whole. I mean, that's what we do. We create the method. We write the software to do it. The software is just the tool, the computer is just the tool, the ideas are the key thing. So yeah, we have to write our own software. You don't get this off the shelf. You ever seen it? That's what we do, is new stuff. That's what's fun about it.
Well, I hate to draw this to an end, but like I said, if you have any questions when you leave here, don't forget to email him. We would love to have you in our department. If you'd like to take classes from Dr. Davis, maybe even do research with him. That's something that's possibly in your future. So let's give him, let's